Yeah, sure. So I will speak on some of the things that me and my group have been interested in the past, say around 5 to 6 years. And I have been working on quantum walks with masters and PhD students of NISQ, and they have done a lot of the work. I have just given them the ideas how to proceed. So this work is based on 3 papers which have been published in the recent past. One was on order from chaos in quantum walks on cyclic graphs. That was with my master's student Abhishek, and that was published in Physics Way. And then with Dinesh, who is doing his PhD with me on maximally entangled single particle states, again using quantum walks. And finally, very recently, we have published a preprint in the archive with Aditi as well as Dinesh on how to implement these cyclic quantum walks on quantum computers. Okay, so here are my collaborators. So Abhishek, who did his master's with me, is now doing his PhD. Dinesh and Aditi are doing their PhDs. Dinesh will be completing his PhD very soon, and Aditi has just started. So basically, what is a quantum walk? So quantum walk, if we know what is a classical random walk, then it's just a quantum version of that. So if you start and you implement a classical random walk, then what you do, you toss a coin, and then you move one step to the left or to the right. That's what is shown in the left column here, depending upon whether it's heads and tails. And you get a nice symmetric distribution around the mean, that is the 0 position. Now, if you do the same thing with a quantum walk, then you have to implement it using quantum states, where it is represented as a ket here. And you have to use a shift, again, the shift operator. The coin operator, which should be a unitary one, is given here as a Hadamard. You can take any arbitrary coin operator. And then the entire evolution is given by the coin operator acting on the coin basis of your quantum state, while the shift operator acts on the position basis of your quantum state. Here represented, the coin basis here is in the 0 state, and the position basis here to start the quantum walker at position 0. And you repeatedly evolve your quantum system, your quantum state, and at a large interval of time, you'll find that it leads to an asymmetric distribution. Now, that is not easy to see when you are doing it for 1 or 2 steps, because for 1 or 2 steps, it's still very much asymmetric. The asymmetry starts from the 3rd time step. You can see it's 18185 probability of landing in position 1. And then when you go on, you'll find it becomes wholly asymmetric. But this hides a very important fact that while the classical random walk, the standard deviation, if you calculate, goes as square root of t. That t is the number of time steps. The quantum walk spreads as t. That is it's much faster distribution as compared to the classical random walk. And these are the classical random walk at say 100 time steps. And this is the quantum random walk in the pink, which is also at 100 time steps. So the advantage with the quantum walk gives us is a very fast spread. And that can be utilized in search algorithms and many other algorithms where quantum walks, if they are implemented in quantum algorithms, they give us a better result as compared to the classical algorithms. So now I showed you that it is a asymmetric probability distribution. Now, if I had taken a equal superposition of my initial state, such as this, then I would have got a symmetric probability distribution as well. But the spread in this case too would be going as t, not as square root of t. Now, our interest in quantum walk started with a game actually. That's Pareto's paradox or the Pareto game. What is the Pareto game? The Pareto game tells us that if I have 2 losing games, can I combine them with some order or some disorder in some arbitrary manner such that I generate a winning game out of 2 losing games? Now, here is a small example. There are 2 games. If the amount of money that player A has even, so let's start the game with player A having 100 rupees, Then if it is even, he gains 3 rupees, so it goes to 103. And if it is odd, which is now it is 103, then he loses 5 rupees, so it becomes 98, and so on and so forth. So if you repeatedly run this game, you will find that every turn he will slowly start losing, and at the end of the process, you will see that he would have lost. The game 2 is at every turn, player A would lose rupees 1. Now, obviously, in game 2, he would lose all his money after 100 turns. But now, if I play it in this manner, that I play game A first, then I play game 2, then I play game 1, and I repeat this, what happens? He starts with, say here, 200, that's an even number. Then after the first turn, he has got 203. So the next turn, he would have a reduction in 1 because he's playing game 2. And then again, every turn he wins. And then finally, you will see this alternate reduction and increase will finally lead him to win in this game. So basically, using two losing strategies, you have won. And this has a lot of applications in biological processes like molecular motors in cells and everything. Our idea here was to see if these kind of Parendo's paradox can be replicated in quantum games. And that's what our initial foray into this business of quantum walk started with student Jishnu, who was also doing his master's. We showed that if my quantum state is a qubit quantum state, then and here we define losing and winning in a slightly different way. We define losing if it lands about the left, the final end position of my walker is towards the left of the origin, is losing. And if he ends up at the right of the origin, he is winning. So there are two, and here the coins which we play with are some unitaries, some arbitrary coin operators. So here we have the C, which has these angles here, pi, pi by 2, pi and pi, which represent, if you parameterize any matrix, you will use these kind of angles. So these will give you a losing game in both cases. If you play only with coin A or with only coin B, as you see here, the median of the probability distribution lies to the left of the origin. It's somewhere in the negative. But when you play one after the other, like A, B, here we are playing BA, BA likewise. So you end up at the right of the origin. So using the same Parendo's principle, we can show the quantum version of the quantum paradox. And this got a lot of notice in the popular science press. Later we said, can we now do something which was shown classically? Classically, it was shown in this PRL work that if you combine two chaotic quantum walks, you can generate, chaotic classical walks, you can generate ordered quantum walk. So this is the first part of my talk, where we will see how to generate an ordered quantum walk by combining two classical chaotic walks. So what we use is we now, instead of a 1D line where we implement our quantum walk, we'll look at implementing our quantum walk on cycles. So here is a 3-cycle and here is a 4-cycle graph. So if you play some game using a coin, so here you are building your cyclic quantum walk with coin with unitary A, you get a chaotic probability distribution. And here what do I mean by chaotic and what I mean by ordered? If the walker periodically returns to where he started from, then it is the ordered quantum walk. If he never returns to where he started from, that is with probability 1, I mean, then it is a chaotic quantum walk. So if we work with coin A, I repeatedly evolve with coin A and a similar shift operator as I showed before, then I will never return with probability 1 to where I started from. Say I started from the origin, I will never return to the origin with probability 1. So this is a chaotic quantum walk. Similarly, if I use coin B, which is another coin, I never return to where I started from. So this again is a chaotic quantum walk. And in this paper in Fitzgerald way, I with Abhishek showed that if you combine these two chaotic quantum walks, you generate an ordered quantum walk where the walker periodically returns to where it started from. And we showed that it has many applications, and I will go to some of the applications. One was on cryptography. Okay. So what's the math behind it? So the math is we have a coin operator. So it has been parameterized using the amplitude here, which is rho, and alpha beta are the phase angles. They can be anywhere between 0 and pi. This is a shift operator, which was earlier the very similar shift, but now there is a mod because it is a cycle. So you have to return to on both sides. So it can be anti-clockwise and clockwise. And then you build your unitary operator combining the shift and the coin. And for n steps, your unitary would have you have to multiply, you have to take the power with n. Now, if the walker returns to its initial state after n steps, then as I defined, the quantum walker is said to be periodic. And therefore, for a periodic quantum walker, this unitary operator after n state should be nothing but an identity. And this is what we see here. If I calculate the eigenvectors of my corresponding eigenvalue, then I get this relation. After applying the unitary operator uk n times on the initial state psi I will express it in terms of my eigenvalues and my xj's, which are the ket operators, expressed in the eigenbasis of the eigenvector. Then the condition for periodicity would be lambda j to the power n is identity, or the unitary operator is identity. So if I can solve my problem of ukn is this identity operator in the 2k, then where I2k is just the identity operator, and then I can find the rho and alpha beta values for which this is satisfied. And that is what I exactly do. I find the generic rho alpha beta values which represent the amplitude at phase of the coin operator, which will satisfy this condition. And depending upon that, I can find out for which coins will get a periodic quantum walk when they are combined in, say, some deterministic fashion. Now, to do that, there is a if you have done your cyclic graph theory in your undergraduate, you will know there's something called a commensurate Fourier matrix, which diagonalizes your unitary matrix. So using that, if you can diagonalize, you'll simplify your problem a lot, and then your finding your eigenvalues becomes much easier, which are just this. And from here, I can find, because this is just gives you a unitary, the appropriate rho alpha beta, which gives you the periodic quantum. So that is what we did. We started with some arbitrary coin operator, which is a unitary A, which is this rho 1 alpha 1 beta 1. We combine with a B operator from game B, which is with amplitude rho 2 and the phase alpha to beta 2, and the coin operator, which is C, which is a combination of rho 1 and the coin AB, which will generate for us the periodic quantum walk. So if I solve, I find that depending upon my A and B values, either I'll get a trivial solution or a non-trivial solution. A trivial solution is one where A is B, so I get back to where I am from. So that's not a proper solution. So I have to find a non-trivial solution where A is not equal to B, which gives me a periodic quantum walk. And you do the calculation. There's some little bit of math involved, but it is very straightforward. And you can find the angles by solving these equations here for the amplitude. Here I take the phase alpha beta to be 0. That makes the solution much easier. So rho 1 is your coin A, and rho 2 is the amplitude of coin B. And I get 3 equations, and there are 2 unknowns, and I can solve them exactly. And there will be many solutions actually. So here I have one solution here for the 3 cycle graph. Similarly, I can do for the 4 cycle and get my rho 1 and rho 2. So for rho 1 and rho 2, I get these amplitudes for the coin operator, and for alpha beta, I take this 0. And I can see that these are equivalent to the, for the 3-cycle graph, the rho, which gives us an ordered quantum walk. And here you can see that both AAA land up in a chaotic quantum walk, and BBB also repeatedly applying it lands up in a chaotic quantum walk. But their combination in this deterministic manner, that is AABB, lands us in a ordered quantum. And as I said, this we can check. One thing to check whether it's truly chaotic or not is not just from the periodicity, but what is called the Lyapunov exponent. If I can calculate the Lyapunov exponent, a positive value of the Lyapunov exponent, it would imply that my walk is chaotic. And if my Lyapunov exponent is 0, then it is periodic or ordered or non-chaotic. So exactly similarly, I start this calculation and I find that for the process AA, it is chaotic, it's small, but it's positive. For process BB, it's again chaotic. But for AB, at exactly 20 time steps, the Lyapunov exponent is 0. So we have got an ordered quantum. So what's the summary of this portion, the first portion? I didn't show you graphs for the 4-cycle graph, but they can be easily done. So in both 3 and 4-cycle graphs, in the paper we have shown, quantum chaotic walks via Parandov strategies were controlled to generate ordered quantum walks. Okay. And then in the same paper, Fizre with the student Abhishek, we showed that we can formulate some cryptographic protocols based on this Parandov scheme. And I will expound on this when I go to part 2 of my talk. So this ends the first part of my talk. If there are any questions, I would like to take them now. Or else I move to part 2 of my talk, which is on generating single particle entangled states using this cyclic quantum box on cyclic graphs. Okay, since there are no questions, we move on to the second part of my talk. So generally, when we talk of entanglement in quantum information, we talk of 2 particles or multi-particle entanglement. But here I will talk of a novel entanglement. Well, not so novel actually. It was first realized by this Nobel laureate Wineland in 1996, who said that can a particle be entangled with itself? What does that mean? That means can entanglement be formulated between 2 distinct degrees of freedom of a single particle? Say a photon, its polarization and its spatial mode are 2 different degrees of freedom, or the spin and position of an electron, that is the spin degree of freedom, and the orbital degree of freedom of an electron are 2 distinct degrees of freedom. Can I generate entanglement between these 2 distinct degrees of freedom? And Wineland in 1996, using cold-trapped single beryllium ions, did just that. He fashioned an entangled state, which here is in the form of a Bell state, between the spatial, local spatial position and the electronic state of that single atom. And he got the Nobel Prize in 2012, and that's where we get our idea whether we can generate entangled states, quantum mechanical. Now, you can read more about single particle entanglement in this science paper. Just okay. So in this paper on science, you can read more about this single particle entanglement. Now, what are the advantages of single particle entanglement over 2 particle or multi-particle entanglement? Well, the first thing is it enables us to encode much more information at a single particle level. That is, our resource requirement is less. There we have at least 2 or more entangled particles you have to. Here you do it using just a single particle. And if there are 3 degrees of freedom, you can entangle 3 degrees of freedom of the particle itself, which we did actually very recently in another Fizre article, which I have no time to discuss, again with Dinesh. Now, robustness. Contrary to interparticle or 2-qubit entanglement, single particle entanglement is much more robust against decoherence. Obviously, where you have no 2 particles separated in distance, here you have a single particle, single the 2 degrees of freedom. So obviously the decoherence and dephasing would that much be reduced. And therefore, and what are the applications of this? So single particle entanglement has applications in analysis of states of photons, and then in engineering single photon quantum devices and photonic quantum information. And as we'll see in our works, we have both cryptographic protocols as well as entanglement-based protocols, which are based on single particle entanglement. And if you want to read more, you can read these two review articles on that. Now, what is our motivation for the second part of the talk? Now, many manuscripts have reported that discrete time quantum walks on lines could be efficient tools to generate maximally entangled single particle states. So one of the first works was by these people, and they showed, you can see here, they calculate the Schmidt norm, which is a measure or an indicator of the amount of entanglement in single particle states. So here they have Adamard and then some random points, and they see maximally entangled single particle states at particular values, say here, or at particular time steps. They reach single particle states. Now, the one thing is that they have a large number of coins they use. So therefore, and they take an arbitrary distribution of initial states, and the coin parameters is not resource saving. That is, it uses n coins. So n different coins means n different gates if you want to implement it and experimentally using photons or in a quantum computer, wherever you want to. So it's very difficult to experimentally. Now, later on, these people in this Fitzroy way came up with a better proposal, and they showed that for any initial state, they can generate maximally entangled single particle states between the coin and the position degrees of freedom, and they showed maximally entangled between the quantum walker for the third step and beyond, and it's regardless for any generic initial state. And but they have two coins. One is, of course, it's a trivial one. They have a Hadamard, and another one is just the identity. Now, we also, in our previous work, we proposed that in a 1D line, we can generate maximally entangled single particle states, but again with a Hadamard or a Fourier, that is with two coins, or a Hadamard or a NOT gate, or a maximally what is this? This M gate and the Fourier gate, and we propose that we will get a maximally entangled single particle state within 10 steps. But in all these cases, we have either two coins or a one coin with identity. So our motivation was, can we have a single coin implementation of MESPS, which will also work for large time steps too? And that's exactly what we did in this work. And so we took arbitrary 4-cycle, 8-cycle, 3 and 5-cycle graphs, and we took a generic coin operator, and obviously this is the cyclic shift, and we evolve it in time, and this is an arbitrary initial state, so we don't take specific initial state, so that's totally arbitrary, and we calculate the Schmidt norm or the von Neumann entropy of our state, and we calculate the entanglement between the coin and position degrees of freedom. And if it's a maximally entangled state, it would mean that the von Neumann entropy is 1, or the Schmidt norm is 1.4, which is basically square. Now, as I said, on cyclic graphs, quantum walk is ordered or periodic if the walker returns to its initial state, and we take advantage of that, and we generate what are called recurrent maximally entangled single particle states. And we show it here. So this is a single coin, and we show it for any arbitrary separable initial state, where t equals to 0, we have a completely separable initial state, and a broad range of coin parameters. So gamma and phi, which are the coin angles here, can be from any value between pi/2 and 3pi/2. So they yield MESPS at t equals to 1 for any arbitrary initial state. And then we showed it for even cycles, that is 4-cycle and 8-cycle, with parameter values satisfying this condition, that we get maximally entangled single particle states, not just at t equal to 1, but at subsequent time steps. We showed theoretically a proof, which is going to be too much to go through it, but if you can read our paper, where we showed exactly how we get that. And these are some plots where we show this is R4, which is a very specific single coin, Q and R8. 4 here means on the 4th cycle. So, and 8 means on an 8 cycle. So it showed that both for even cycle graphs with a single coin, we can have maximally entangled states, which you can generate in single cyclic quantum walks, single coin cyclic quantum walks, and therefore any arbitrary coin, basically R4, Q4, and many other coins we gave examples of. Now this can be easily experimentally realized using quantum walks with photons. So what you do is you encode the quantum coin state in the photon's polarization degree of freedom, that is its horizontal or vertical degree of freedom. The Walker position is encoded in its the photon's orbital angular momentum. For coin operations, you use half-wave plates and quarter-wave plates, and for the shift operation, you use something called a calcite beam displacer. And using that, you can experimentally realize this proposal. And this experimental implementation of cyclic quantum walks with single photons has already been shown. So our protocol is feasible, very much feasible. And we also show how to generate a cryptographic proposal. What we do is we want to transfer some secure message between two parties, here Alice and Bob. And this message is encoded in the sites of our cycle. Here are 4 cycle. And Alice wants to send any of these messages, 0, 1, 2, 3, to Bob. Then Bob generates the public key by applying the coin on the states of the Walker. Initially, they are unentangled. So he applies this Hadamard coin 5 times. And he generates a state, and which can be maximally entangled or not. And after generating this maximally entangled state, which acts as a public key, he sends it to Alice, and Alice now encrypts this message by using this shift operator, and then sends the message back to Bob via quantum channel, and then Bob decrypts the message by operating the rest of the Hadamard gates, and then gets the identity. And then there's a trivial shift to get back the message. So this works, and this we showed it in that. So to summarize this second part of my talk, we generate controlled entanglement via cyclic quantum walks on even cycle graphs. For odd cycles also we show, but in odd cycles we have to use effective single coin, that is one coin and along with identity, to generate maximally entangled single particle states. And of course this is the most straightforward because it is the most least resource consuming and the easiest to implement experimentally. And yeah, so important note that our even cycle results were implemented and verified on a NISQ quantum computer by these chaps in this entropy paper. And this was the motivation to look into whether we can implement the first part of our work on generating order from chaos in a quantum computer too. So this ends the second part of my talk. So if there are any questions, I would be happy to take them now before I go to the third part of my talk. Okay. So yeah. Sorry. Oh, okay. There are no questions. Okay. So somehow I've not been able to motivate people too much. Anyway, but feel free to interrupt me and ask questions anytime you don't understand something. Okay. Anyway, so this is the third part and the final part of my talk. So how to implement or verify our protocols on a NISQ device. As I showed you, our proposal, which we published in Fizreville Letters, was verified on a NISQ device by Razzoli et al. Now, our idea is to implement the order from chaos work, which I did with my master student Abhishek, And we showed that we can do a NISQ implementation of our protocols for both even and odd cycle graphs. And I will talk to you about the circuit and how we do it in both for even and odd cycle, and what are the metrics. So there are two metrics. One is the depth of the quantum circuit. The lesser the depth, the better, because each layer of depth increases errors and other things. So we want the depth should be lower. And the fidelity, how good is the match between the exact result and the replicated result on the quantum computer. So if the match is good, say above 99%, then it's good. And if the match is bad, then how to improve it. And we show that in even cycle graphs, the fidelity is very good, almost better than 98, 99%. But for odd cycle graphs, I will show you that the fidelity of our results are not that good. So how to improvise it, we'll show a scheme, we'll explain to you. That is called dynamical decoupling, by which we improvise. Okay. So here we start. Now, the results which I showed to you before were implemented all on classical computers. We run a quantum walk-based algorithm on a classical computer. So you may ask, if you can run your quantum walk codes on Python on your classical desktop, then why you need a quantum computer? Well, the answer is, in the classical simulation, we use simple linear algebra to do the calculation, and that is mapped by a machine algorithm in C or whatever to the classical computer, and it uses a wide basis. So if you have a single qubit basis, because there are infinite number of states theoretically, depending upon at how many values of your angles you give, say 1,000 points or 1,000,000 points. So your classical computer will break that column vector into 1,000 rank column vector and calculate. So that in this type of thing will scale exponentially with the number of qubits. So if you have a cyclic graph on 4 sides with a single coin, that would be very easy in a classical computer. And in fact, there would be no advantage of doing it on a quantum computer. But if you go to, say, a 1D line, or even for a 1D line, it's not that difficult. But if you go to 2D line, for example, in our PhysRev work with Dinesh, where we are trying to implement it on 2D graph, so we could go maximum to, say, time step 20 time steps, and that was to take 8 or 9 days to do on our nicer HPC. So that is exponentially, it scales exponentially with the number of qubits, and it's extremely memory intensive. So how are you going to simulate quantum walk when you are going to 2D, when it is so difficult, even for 20 time steps to simulate it in a classical computer? So it's extremely difficult. So we want to, if you can do it on a quantum computer, that would be very easy, because a quantum computer will map each of the superposed state to the superposed state of the machine algorithm which runs the quantum computer. So because of that, we want to implement it on a quantum computer. So this is basically a proof of principle. If I can implement a simple case like a cyclic quantum walk on my quantum computer, I can do bigger cases. Of course, we'll see that even for this simple case, the fidelity for odd cycle graphs is pretty bad. So we are not in the stage where we can, with 100% accuracy, implement something in quantum computers till now. So as I said, our aim here is to use quantum computers because they are the natural bedrock of our algorithms, and this obviously they will take much less time than your classical computer, and it is relevant how we build our new quantum computers. If we can, with great fidelity, do small projects on quantum cyclic graphs, then you can scale it up and do it for larger projects like 1D line or 2D graphs and other things. So what are the approaches to implement pure TTQW? So basically, what you do is, this was the first proposal. It was a controlled increment. So what you do is you basically have to implement your shift operator in your quantum computer. The coin operator works on a single qubit, whether it's a single qubit operator like a NOT or a Hadamard, whatever. So it's directly applied. But for the shift, which is the position, you have to encode it in that many more qubits. If it's for a 4 cycle, which has so you need just 2 qubits, because 0, 0, 0, 1, 1, 0, and 1, 1 are the 4 states of the 2 qubits, and they can be easily mapped to the 4 sides of your cycle. So you need for 4 cycle basically 1 qubit for the coin and 2 qubits for the position, and with that your job is secure. And what this Douglas and Wang did was an increment decrement circuit, which it's a 1-to-1 mapping of your shift. And how they implement this shift, the coin operation by a single qubit, and the shift operator is mapped using this increment. So if the coin operator lands you in a 0 state, then you increment the position qubits by 1, and if the coin operator lands you in the 1 state, you decrement. Now you can do it sequentially. That will lead to larger circuit depth. But if you do it parallelly, that will lead to lower circuit depth. So what they did was they did it parallelly. So both increment and decrement worked on the basis of the coin state. So the circuit depth was not that much. Your circuit depth refers to the parallel operation of the gates. So this was the first proposal. The second proposal is, so again, continuing on the same proposal. So here, so they implemented it even for large cycle graphs. So here's a 16 and a 25 cycle graph. And so efficiency is based on how the qubits or resources scale as the system size increases. And the metric which we determine how good is our protocol to implement in a quantum computer is the number of sequential gate layers here. As you see, the increment is done using some control NOT gates, as we see here, which are Toffoli gates. And then there are control NOT gates also. Now, all these gates increase errors because control NOT gates are extremely error sensitive. So they lead to a lot of errors. So always our aim is to reduce the number of 2 qubit operations and replace this control NOT operations using single qubit gates. So unfortunately for this proposal, if you see that the circuit depth is not that large, especially for it scales as ON square T, that is N is the number of position qubits. As I said, for 4 cycle graph, N is your 2 qubits. So it goes as 4T. So for time step T equals to 1, the circuit depth is 4. That is basically there are 4 layers of gates which are operated sequentially. And that's not that bad, but what are the gates here? So the gates here are control NOT, as I said, which lead to a lot of errors. So we don't want these kind of gates in our circuit. The second proposal was developed by these people, by Shakil, and then it was optimized by Razzoli et al. And this was again for TTQW on cyclic graphs, but they only showed it for even cycle graphs. So what they do is by a nice twist, they change the shift operator by using some quantum Fourier transform operators, and which they diagonalize the shift operators. Now, as we saw before, the shift operators were implemented using control NOT and control NOT gates. So using this, they reduce they eliminate actually the control NOT gates. They mainly use single qubit gates. There is some CNOTs they have to use. And the first proposal by this Shakil used quantum Fourier transforms at each time step. What Razzoli et al. Did was to optimize it. They only used it at the beginning of the process and at the end. So not at each time step, but at the beginning of the process and at the end. So while the Shakil used more quantum Fourier transform and inverse quantum Fourier transform gates. So that was a major improvement on how to implement cyclic quantum walks on quantum computers. And if you want to read, you can read more about it in these 2 papers. And what are the key differences between these optimized quantum Fourier transform protocol and the controlled increment-decrement circuit. So here its approach is based on quantum Fourier transform, with which you diagonalize your shift operator. Here the shift is implemented by Toffoli gates and control nodes. The circuit depth is 4, and circuit depth here is also very less. This is for one time step. And the scalability, it is very efficient for all even cycles. For all even cycles, as we have checked, its fidelity is more than 99%. It's general. You can implement both odd and even, but it's extremely bad as far as fidelity is concerned. The errors are very high. So here are some values for your gates. Here without transpilation means without using in the because when you do in the modern quantum computers is this NISQ device, you have to what you do is to transpile them. You have to convert whatever gates in your QSQT based proposal to a native set of gates. So without that, you can see this is after 20 time steps. So effectively, this is around 7, while the quantum Fourier transform protocol of Shakil is around 8 time steps. Sorry, 8 circuit depth of 8. While for the optimized QFT of the Razzoli et al. Is just 2 or 3. It's very much reduced. So here you can see. But in the quantum computer, which you use native gates, you increase the number of gates, and therefore the circuit depth increases. But after 20 steps, here it's actually it should be somewhat different because the optimized QFT actually has inbuilt. It can efficiently implement the periodicity of the quantum walk too. So it gauges the periodicity and finds the optimum circuit depth for it. So for the circuit depth here, if we have a 4-cycle graph and using our coin operators, we find that the periodicity is 5, periodicity is 20. So here you can do it using a depth of 5. Actually. So that gives a rapid improvement for optimized quantum Fourier transform circuits. So this is a circuit implementation. This is the IBM share group. This is the qubit connectivity, and you use only 3 of these qubits, one for coin, the other 2 for position. And this is the QSQT based circuit. And this you can see the layers. This is I imagine for 4 time steps. So you can see basically there are around 3 to 4 circuit depth for each time step. And I said that there is one metric which is the circuit depth. There is another metric which is called the Hellinger fidelity, which is the comparison between the distance between 2 probability distributions. So if I have a probability distribution which is obtained in an ideal quantum walk simulation in an AER simulator, and Q is the probability distribution in the IBM quantum device, then how much is the distance between these 2 probability distributions? So this Hellinger distance measures the difference basically. So if it's a fidelity of greater than 95%, then basically they're almost alike. And as I said, this is the QSQT based framework with these gates, this quantum Fourier transform gates and this single qubit phase gates and all, with which you, and this A is the coin gate. You have to convert this gate into the quantum computer usable gates. So the quantum computer uses some different set of gates. So it has to have a 1-to-1 mapping between our QSQT based gates to this quantum gates, and these are some of the gates which they use. And after the transpilation, actually the circuit depth increases. But these, and the reason one uses this is because if we use those gates to work on this quantum computer, the errors will be much more. So to reduce errors, you work with the native gates of the quantum computer, and of course the circuit depth increases, and these quantum computers can run on different levels of optimization. So if you put optimization 0, then basically you are running on the QSQT based gate. So it preserves that QSQT gate structure, and depending upon how much optimization you want and whatever results you want, you can go for a light optimization or a medium optimization or maximum optimization. So we ran our codes both on both light optimization and also heavy optimization, and we saw that if you heavily optimize your circuit, then you get the best results. So here we have results for even cycle optimization, And you can see the probability of our AR simulator. Here, the green lines are for noisy, so you arbitrarily add noise to your QSQT-based code, and then you run it on your IBM Sherbrooke, which is the NISQ quantum device, with the optimization level of 3. And you can see the probability distribution is fairly perfect with very small errors. And you can see this Hellinger fidelity, which is like more than 99.5%. Yeah. And so in general, it's above 98 for all time steps. But for the periodicity, it captures it with a great fidelity of almost 98%. So, and then we can also do, so I told you that a problem with the QFT based protocols was that it couldn't capture the odd cycle, and we also see that in our case, in the odd cycle case, it isn't able to capture the fidelities properly. The fidelity reduces drastically to around 65%, and you can see the probability distribution also go down heavily. And one of the reasons is when you do the QFT transform, you have to leave one state unused. Now that gathers errors. So what to do is you use what are called dynamical decoupling pulses, so that this state is left unused. And these are the 4-cycle results for the depth. So these are for 3 cycle now. So if I optimize my QFT protocol with dynamical decoupling pulses, my fidelity improves overall to 95% from 90. And for 25 time steps, so the fidelity at periodicity time is equal to 20. It increases from 90 to 95%, and overall fidelity from 65 to 75%. So here's the summary of the third part. So the algorithms, we want to use our algorithms to run these codes. You can find it in the archive version of our paper. And we have realized the transition from quantum chaos to order by a discrete time quantum walk on both odd and even cyclic devices. I only showed the results for IBM Sherbrooke. If you go to the appendix of our paper, we will find results for both IBM Kiev and IBM Brisbane too. And we see for 4-cycle graphs exhibit very high fidelity, almost like 99%. The 3-cycle implementation, the fidelity does improve when we augment it with dynamical decoupling pulses. So at the end, we have demonstrated a practical approach, probe and harness control chaotic dynamics on real quantum hardware. And this lays the groundwork for, we are actually working on future generating quantum entanglement protocols on odd cycle graphs, and also on cryptographic protocols on these NISQ devices. And these works are currently on, and we'll hope to report them soon. So thank you very much for your attention. And, yeah, thanks.
Yeah, let's thank the speaker. And now we will session with the for discussion. Any question from the audience?
Hello, sir.
Yeah.
I had a question.
Yes, sure.
You talked about removing the C0 gates. You have also been using transpilers to optimize the circuit.
Yes.
So if I am using C0 gate and then using transpiler to optimize, will I have the need to remove the C0 gates?
Sorry, I couldn't get you. What's the last thing you said?
I was saying that like we are removing the C0 gates. So if I don't remove the C0 gates,
I think without C0s also you can do it. But in the optimized QFT, they do use a few C0 gates, or they convert it to ESR, something like that. I am not very sure about that. But yeah, see, we want to reduce 2-qubit gates because these gates increase errors. So the best algorithm would be without using any C0 gates if you can do it. The optimized QFT doesn't use any Toffoli gates. There is control not, but it still uses a few C0 gates if I am not wrong. Yeah, if we can eliminate all CNOT gates, that would be the best. If you see, there are in the QFT only at the beginning and at the end, I think they require a CNOT. Other than that, they don't require CNOTs.
I wanted to know, like, if does the transpiler also remove CNOT gates for optimization? Because
I think the transpiler, the native gates of the transpiler. Well, there is a echoed cross resonance gate, which is the equivalent of the CNOT gate, which the transpiler circuit does use in the NISQ hardware, which is the equivalent of the CNOT, you can say, yeah. But it's not exactly same as the C.
and do you know how much like CNOT gates is okay to use for quantum algorithm? Like,
The less the better. The less the better. If you can reduce the CNOT gate, which is a 2-qubit gate, to almost minimal, it's the best.